I have the distinct pleasure of introducing today's speaker. And I know all of us are really excited, and the people on the Zoom are really excited about our speaker today. A little bit of background. A couple years ago, well, let's see, 8 years ago, one of my dear friends met this man. And when I found out what he did for a living, I was like, wow, that's really impressive, right? Couldn't understand half of what he was saying, but I was very impressed. And then when his wife's daughter married my son, I got really excited, because at my age, 3D body parts at a discount? Maybe this is something I want to be doing. And then, of course, to seal the whole deal, when my son and his wife's daughter got married, that woman right there was the officiant. So we just keep it all in Rotary, right? Dr. David Dean spent nearly 20 years at Case Western Reserve University, where his primary appointment was in the Department of Neurosurgery in the School of Medicine, where he led the department's imaging laboratory. In 2013, Dr. Dean joined the Ohio State University, where he has full faculty appointments in both departments of material science and engineering in the College of Engineering and plastic and reconstructive surgery in the College of Medicine. That's an important thing to know when you hear him talk. Dr. Dean directs the Osteo Engineering Laboratory, which focuses on the design and fabrication of personalized medical devices for reconstructive skeletal surgery. And I checked, facelifts are not included in that, ladies. His laboratory research includes 3D imaging, 3D printing, and skeletal repair device manufacturing. These techniques used to manufacture these devices range from 3D printing of living material to 3D metal printing. Dr. Dean is an author of many journals and of 2 books. He's a member of 7 editorial boards and an inventor on 18 issued patents and 18 pending patents. Dr. Dean has played a role in founding 4 companies for the purpose of practicing the technology that Dr. Dean invented. So would you please all welcome Dr. David Dean.
Thank you for the very nice welcome and the kind invitation. It's an honor to be here. Oh, thank you very much. I'm going to try to be as efficient as I can with our time, and probably you'll need to watch the screen over there. Those of you online, I'm sure, can see the screen over there. The title of this talk is, for you right now, most likely a bucket of words, and I'm hoping that at the end, especially the first 3 words, have some significance in regards to reconstructive surgery, and that the sentence that follows those words, you understand what we're doing that's new in terms of personalizing medical devices and making them at the point of care. So both of those are relatively new, but especially the latter is extremely new. So 3 parts, and I'm going to try to hold to way less than 10 minutes for each, because I know I have half an hour. So personalized design, what is that and why would we do that? And just first disclosure, as Joanne just mentioned, I may be perceived to have a conflict, and I'm managing that with the university. Again, I have technology I'm going to present to you that's licensed by companies, but I think I'm non-conflicted in giving this talk. So hybrid, why the word hybrid? The word hybrid refers to using whatever manufacturing method that is available to us that makes sense and is going to get us the performance of the device, rather than using what is available in a factory, and I'll get more into this later. So there's old school manufacturing, what Henry Ford did, and what we're doing now is not like that at all. We're not, and the terms that I would use now, manufacturing for design, that's what we're doing. Design for manufacturing, that's designing something so that it can be made on an assembly line. We're not doing that. Autonomous. So autonomy means away from the factory, right? The factory is where the physician and the engineer are sitting, and the physician has some input into the design. That doesn't happen now, or at least very, very rarely. I've already mentioned the assembly line-based manufacturing, and the reason for going to these great lengths, to being able to design something at the point of care and to be able to manufacture it at the point of care are two. There are people who would benefit from personalized medical devices, meaning custom fit, custom performance, that don't have a chance to get them now because their treatment has to happen too quickly. Late-stage cancer, trauma. We don't have enough time to wait for something to be personalized from a factory, to have the engineers involved and ship it and all of that. The other reason to be doing this, to be bringing personalization to more patients, is we have a lot of devices and therapies now where there's a high failure rate. There's a high amount of revision surgery, and that's standard of care. The reason that's standard of care is because it beats the alternative, right? You get a hip implant so you can keep moving around, as opposed to 50 years ago, you were in a wheelchair, and right? So there, it's always, that's always the reason. The surgeons know what they can do to help you. We're trying to give them better tools to help you. So personalization, better form and fit, but also function. 3D printing is how most people think personalization happens now. It does happen, but that's not going to be enough for us. The way we can 3D print things now, we're not going to be doing nearly as many devices as we could be, and we certainly wouldn't be able to do that at the point of care. There's not going to be a metal printer anywhere near the operating room. That's going to be at a different site. The current devices are not 3D printed. The surgeons really don't hear about that. They're not personalized. They're ready to help you that day, and if they bring anything personalized in, it's because a company has brought them an FDA-approved product and they're going to help them, and they're going to let you make a decision if you want that. So this is where the autonomy comes in. The physician really doesn't get to assess the performance in you. They can, from experience, they can estimate it, but this is what we're going to be bringing that's new, is to be able to personalize the design for it to fit you and to perform in you. And the reason for this, the reason why they can't personalize the performance is the FDA approval process. The companies will bring them something, here are the indications, here's how it's going to work in the patient. Maybe there's some things that prevent some patients from getting it. They try to generalize as much as possible, but not as much as we can. The FDA doesn't like products or machines with lots of knobs on them. They like to keep a design envelope that they have control over. And the FDA, one of the roles, most people may not be aware of this, they're aware that the products get approved by them. They also supervise the manufacturing. They go into the factory and make sure it's happening correctly day by day. So this is what it means to personalize now. And this image is actually, could have been done 10 years ago, 20 years ago, 30 years ago. It doesn't happen very often, but we can't build a widget for a patient. We can't take our current computer-aided design software and just put together cubes and pie wedges and rectangles and circles and make something that's going to help you as an implant. We have to start with you. We have to start with your shape and what's going to fit you, and that's usually coming from some 3D imaging, a 3D MR scan, a 3D CT scan. There are other ways of getting 3D imaging. Then we fit a shape into your defect, either one that exists now or one that we're going to create. And then we have to basically cookie cut out that shape. That's the beginning of the design. In some cases that's enough, but that's very rare that that's enough, that you just send that to a 3D printer and put that in the patient. We're also usually having to do some testing that this is going to fit in you before we get to the operating room. It's too late to get in the operating room and see, is this going to fit? We have to make sure that well ahead of the surgery. So this is 30 years old. So this is from my PhD work, doctoral dissertation, and the goal of my doctoral dissertation was to produce average 3D CT images of the skull. How did we do that? Prior to that time, most of the data collected on the skull was linear measurements collected between landmarks like tip of nose, tip of chin. There wasn't any such thing as 3D surface image averaging. But how were we able to map one person's image onto the next, onto the next? We had to use these sharp features you see in the dark black lines. So the crest lines around the rim of your eye socket, around the rim of your nose, around the rim of the teeth, and so on. That allowed us to tile out the skull and average the tiles separately and then bring them back together. And you can see along the lower edge there, those were all studies done in the late 90s to early 2000s to produce average images. I would collect those skulls that were scanned and then averaged at different parts around the country from either dry skulls or morgue specimens, and I had a letter with me if I got stopped to say I'm not a mass murderer, and bring them and CT scan them, return them to the museum. So here's how we use that data. So someone with this big of a hole in their skull, like the cases we've worked on, it's not optional. You have to have a skull that protects the brain from trauma and infection, and if you have a hole like this for any length of time, you're wearing a very sophisticated bike helmet to protect the brain because it's right under the scalp. So we would take the image, we would identify the region of interest, the area around the hole, map the curvature, red is low curvature, blue is high curvature, we'd find the edge of the hole, and then we would take an image, and in this, there are two sources of images mainly. On the left you see the patient's image just right, left mirrored, and you can see some dark blue dots, and you can see when they were scanned. And again, on the one on the left, the more solid image is the scan, and the translucent blue one is the flipped image. And then we have to merge those two together to fill that hole. And that does pretty well, but not quite good enough. On the right is an average image, and our average images look even smoother than that now. So here's one individual who we did that with, and you can see how through a series of fitting exercises we can get that right-left mirrored image. That only works if the hole is all on one side. If you're mirroring across a defect that's crossing the midline, you're going to mirror hole to hole, and that doesn't help. So we've done this with many, many patients. These are patients and developed a number of tools. And could you play the movie for me? This is one of two movies. This will show you that matching process. So we find the crest line around the edge of the defect on both images, the mirrored one and the patient's image. And then we do a quick warp and bring them together. There still is some area that's not quite fitting well. And we go in and you can see control points on the surface and make sure now you can see after the second warp it's fitting much better. And now we have the outer surface of what the implant needs to be. We have to add some thickness to that implant. It has no thickness right now. It's just the outer surface. Those average images or even the right-left mirrored, it's just the outer surface. And this is what we have to do with that piece that we cookie cut out. We regularize the surface. You can see now it's a nice grid. And we add some thickness. And you can see the area we've added, the thickness, that red area is what's going to be in contact with the patient's skull. We want it to sit there like a jack-o'-lantern top, really lock in tight. We're still going to add some plates and screws to hold it in place. Now we bring it back to the skull with the added thickness, and we bring back the brain, and we'll bring back the scalp as well. And we make sure it's not pressing on the brain, because if it is, you can see the dura mater, the outer lining of the brain, it's going to cause seizures. So we make sure that's not going to happen. If it's pushing out on the scalp, it'll pinch off the arteries that supply the scalp, and the scalp will die. So we make sure that both of those don't happen. So here's one where it's pressing out on the scalp, and that's an easy fix. You just suck the implant back in a little bit, and it's not pressing on the scalp anymore. These steps are very quick. And here's a bunch of patients. Now, I just show you these images because there's some interesting things. The one all the way over on the left, that one crossed the midline. And that's a surgical removal of bone. Could have been an aneurysm, could have been a tumor. I don't even recall which one it was. And then we had to put an average shape in there because we had nothing to mirror across the sides. The other ones, you can see the images along the top, those are right-left mirrored. And when we mirror something from CT scan data, you can see we also mirrored the slice edges. You can see they're a little bit stair-step, they're a little bit jaggy. So at the bottom row, you can see they've all been smoothed, because if we left those sharp edges, when the chewing muscles would be moving, they'd be scraping across that, and the patient wouldn't like that. So those are the final post-processing steps in these implants. I don't say this lightly. We 3D printed the first cranial implant from a CAD file. In secret, under an internal review board protocol. Confidential, the patient knew we were doing it, but no one else knew we were doing this. In 1996, at Case Western Reserve in Cleveland, and it went in the patient, and a very grateful patient. We did it 4 more times until I was early in my career, and I was starting to get a lot of these requests. It was very time consuming, and I asked my chair, is this now my job? And he said, and I didn't want it to be my job because I still had to get tenure. I had to produce research, not implants. And he said, no, it's not your job. I don't think we should keep this to ourselves anymore. We should start a company. So we started a company in November 1998. That company is called Osteo. They made implants until 2006, and then they just began licensing the software we use. So personalized performance. So I told you about the biomechanics. The materials can make a big difference. So anyone who gets a hip implant, when they get it, they're told by the surgeon's always going to tell them, if you're around in 10 years from now, we need to look at this again and see if it's in place tightly, and because we know they loosen. And the reason they loosen is because of what you see on the right. So you see the mechanical model there. It's supposed to be bearing weight just under the ball, what's called the neck of the femur, on the side closest to the midline. But when we put a big piece of metal in there, and that's an old style implant that you're seeing on the right, it has a nail at the top that's screwed into the bone. It has a lip, you can see, that's keeping it from sliding into the marrow cavity, which is, in an adult is not actually full of bone marrow, it's full of fat. And scoop that out, put it in there, and it picks up the load at the top, at the ball, and drops it at the knee. And so everything in between is getting no load because the material's too stiff. And that's why they loosen. So it's called stress shielding. You're not letting the bone get the load it needs. Here's a patient. This is a study done with strong collaboration from the chair of orthopedic surgery at Ohio State for Zimmer Biomet. And you can see they have a traditional implant on the left. There's no bone around it. I don't even know how it's there, but I think if you look at this image carefully, at least if I do, the patient's standing on the other leg. That's basically nothing around it, nothing holding it there. On the other side, this was a study where this person had the other implant for 12 years, the old style implant on their left for 17, and you can see it's plastic on the inside and only a thin sleeve of metal on the outside. So much less stiff, much less strong, and the bone is still there around the implant. That Zimmer Biomet calls this their epic implant. Huge difference just because of changing the materials. So the material there is Ti64, which you see here, 90% titanium, 6% aluminum, 4% vanadium. We've been exploring nickel, titanium, and magnesium as newer materials with two colleagues at one at Ohio State, Dr. Lau, and one the chair of mechanical engineering at the University of Toledo, Dr. Alahinia. Nickel titanium is difficult to work with. It has this property called shape memory. It kind of fights back when you're trying to bend it or grind it or whatever you're trying to do to form it. It's used in the stents in the heart. It's used in orthodontic wire. It's drawn wire. But if we were trying to make a bulk device, it'd be very difficult to form. But you can 3D print it, and that's what we're doing. So it's easy to form that way. Here's a study we did in 2015, and all we did was, most people think mandible, oh, that's not a loaded bone. Hip and knee and spine, those are loaded. No, mandible is hugely loaded. You can only chew hard in one spot in your mouth at a time, between two molars. If you're biting steak or a walnut, 200 pounds per square inch, like a woman's high-heeled shoe coming down right there at that spot. And that puts a huge load on the mandible. And this is someone who has a bone graft because they had a tumor in their jaw. This, unfortunately, is more than 50,000 people a year in this country, several hundred in Columbus, who need to have a big piece of their jaw taken out and a graft, usually from the calf, a bone called the fibula, put in, and then metal put on it to hold it while it's healing. Those break far too often. If it's what the surgeons call a hemimandible, it's got about a 40% chance of the plate breaking and everything has to start over again. One of the reasons is the plates not only shield the bone from getting any load, they concentrate the load at local spots because they're so stiff, and that makes it more likely to break. Here you see a simulation where the red load of the metal is not there. It's in the bone where we want it. At the bottom, you see it's mostly blue and green, and that's because the bone is getting the load instead of the plate because it's nickel titanium. It's a much less stiff material than the current alloy that's used in hip and knee implants and even these mandibular fixation plates. So here's showing you the stiffness. We can manipulate the stiffness of nickel titanium by adding porosity, but basically we can make it more stiff than a bone, a little bit or a little bit less, depending on what we want it to do. Here's some work we do with sheep. It looks like a human jaw, but it's actually a sheep jaw. And you can see we take a piece of the sheep's mandible out, put it back, and put a plate on it, and make sure that what we're talking about works. And you see the plates we put on the sheep at the lower right. So coming around the stretch, point of care manufacturing. Why should we care about point of care manufacturing? Well, 19th century, 20th century, it's all about mass production in a factory, on an assembly line. We always attribute this to Henry Ford, but what did that give us? It gave us the supply chain. We all know from COVID and coming out of COVID that the U.S. was in a deadly situation with all of its supply chains being hugely dependent on, too dependent on countries that were having COVID just like us and couldn't get us anything. So the world economy broke, and we've learned that we probably should be forward positioning more supplies and maybe even making them closer to where we use them in some cases, especially mission critical. And so this was well known before COVID, but now we've learned our lesson. And this is, instead of centralized manufacturing, it's called distributed manufacturing. That means we just break the model and we figure out how can we do this, not only at the point of care, but at the point of need. For mission critical, we need to be thinking about how to make things where they need to be used, especially if they need to be used in a hurry. So here's a place where it needs to be used in a hurry. This is on the left, you see, these are all the same pictures. They're actually 3D printed models of the same person. On the left, that was after a horrific traumatic auto accident. And you can see lots of cracks, pieces of skull that used to be together. And this person, they could have fixed them without any help from us. They just start putting together what's moving against what's not moving, and they just keep doing it until it gets done. And often then they have to go in and revise because the face is swelling up like the Great Pumpkin, and it's difficult surgery. If we just take a few minutes and plan where these pieces should go, you get the picture in the middle. And you 3D print it, and then you can bend plates to it, and then the plates guide the surgery. It goes faster. So this type of thing doesn't happen everywhere. It can happen at Ohio State, it can happen at Mayo Clinic, it can happen at Walter Reed in Washington, it can happen at the major medical centers. But if you have this accident 2-3 hours from Ohio State, maybe 2-3 days, they're just working by hand. They're going to get it done, and you will probably have a revision in something like this. It can be a definitive surgery, though, but you can see the bending of the plates on the right. That for this patient would have taken probably a day, and that's going to be done by the surgeon if they have the model. If they're doing it in the operating room, they may have to call in for another team to relieve them because they can only keep their eyes open so long. This is going to be a massive case. So bone grafting, that person probably needed some bone grafts. This is a typical thing where we can use the computer-aided design. This is coming back to that oral cancer. Big piece of the mandible in blue there on the upper left is coming out. We're going down to the fibula, creating a cutting guide to take two pieces, bring them up, make a new face, mostly the jaw, but have the plate ready to go. What about this at the point of care? How is it going to happen? You can see on the left there, this is our vision. We have an NSF grant for a new center called HAMMER. Hybrid Autonomous Manufacturing is the HAM at the beginning of HAMMER. What about using robots? And the picture on the left there, that is a hip implant with 2 robot arms grinding it out of metal. We don't have robots that small and that strong that they would need to be. We have the ones on the right, like the ones they use in factory. So we're trying to bridge that gap between what robots do in factories and what we need them to do for point-of-care manufacturing. So the head of this new center, the HAMMER Engineering Research Center at Ohio State University, it involves 4 other universities, but Ohio State is leading, is Dr. Glenn Dane. His picture's on the upper right. And his newly graduated, Dr. Brian Thurston, his newly graduated student, worked together with us. And what you see here is 2 robots working together, and they're based on a gimbal. The word gimbal is what you see, that picture moving around. So this is what keeps a rocket going in the right direction, or a plane. It's that type of apparatus. So 2 robots that can work together in very close quarters, like we need with small parts that go in patients, are based on gimbals. Our first case, trying to bend a plate for a patient, it happens to be our sheep. And we've done that with this robot. And I'll ask you, this is my last movie. So this is the robot, we call it the Bendy Bot. There's a little bit of sound here. I don't know if you'll be able to hear it, but it works. Oh, it does. So the robot is holding a fixation plate that's going to hold bone together, in this case for a sheep. And you see it's bending and twisting and moving along the plate, and it's going to produce the final bent plate that's going to fit right against the sheep. And this is in 90 seconds that it's gone through from one end to the other of the plate and made the final shape. Something that would take the surgeon 2 hours. because they're either pushing it against the plastic model or the bloody patient and trying to make sure it's flush against the bone. If it's above the bone, it's going to break there. It's got to be wrapped tightly against the bone. So this is 3D printed plastic. We're now reinforcing this, adding metal parts, but these motors are not strong enough to bend the plates we need for that mandibular graft surgery, for example, or femur or humerus or the large bones in the body. This was invented this year, earlier in the year. So I presented this in May for the first time at the Society for Manufacturing Engineers. They were thrilled to see this type of thing could be on a desktop right next to the operating room. This plate is made out of aluminum. To go to materials like nickel titanium or Ti64, we would need much stronger motors. And I think that's the end of the talk. And I just want to thank our sponsors, the National Science Foundation, a number of other private foundations that are listed there, and of course all the people who actually did the work. Time for questions, okay.
You started off by saying that it takes some time to create some of these implants and so forth, and yet you need to do it kind of in the operating room setting almost. Are you at a point where a surgeon can implement this kind of implant pretty quickly?
So there are some custom implants available now, and those will be 3 weeks to 3 months. We've just gotten started on this robot. If we have 3D printing available near the hospital, we were making skull plates in Cleveland in 2 hours in the 90s. It can be done.
So you can react to accidents and emergency situations?
It's just a question of whether you have ISO 1345, what's called good manufacturing practice facility right there, who's able to make what you need.
Thank you.
Please.
I can understand why you might need to have custom manufacturing for something like you were talking about the face. But for hips and knees, aren't the standard ones that they have now, aren't those pretty much good enough?
They're better than the alternative, no doubt about that. Ambulation is really important. No blood gets back to the heart unless your muscles are contracting and you're moving around. So you need to keep moving. Despite your own need for mobility, your body needs you to keep moving. So there's no doubt that's the best choice. That it's going to loosen over time is what we want to avoid. The revision surgery, and people getting them younger and younger. Someone who gets a hip implant in their 40s, they only are doing revision surgeries once. I don't know of them doing them 2, 3, 4 times. So that's what we're really looking at.
I'm just going to add on a happy buck. I've had both knees and both hips done.
When you compare the newer technology that you're looking at to something that's like that, how much longer is it projected to last?
Yeah, so that's what we're trying to do. When you have this stress shielding and the load bypasses the bone, every bone in your body is replaced every 7 years through what's called microfracturing. The load it gets breaks something that you have no idea, no pain, no nothing. And that by that process, where it's weakest now, it becomes new again. And then throughout the whole bone, it's completely replaced that way every 7 years. And even if you're 100 years old, that's going on. So if we can have an implant that redistributes the load, at least doesn't interrupt the normal loading, it is sustainable. Absolutely. Great question.
I've had a hip replaced myself too, and when the doctor told me that after the surgery that my hip socket was the biggest he had ever seen, and he went in with a smaller one, had to change that, until they were down to one left, and that was the one that fit in. But that's my thing. Are we going to get to a point where it's measured and you got the perfect fit in there before you go through something like this?
Your doctor would love autonomy. He'd love to be able to get the fit before, not just pull something off the shelf and see if it's going to fit. It can take some measurements, and then everyone's different, the proportions of things. And that's very common. So the reason he was doing that is he had to get the center of rotation that used to be there. He had to get whatever size the implant was, he had to find that center of rotation, or you would not like it. You would not be able to walk easily.
And that's something you can't do, because I know.
We can plan it.
And everything beforehand.
We can plan it if we can do customization. Planning it doesn't matter, though, if you have no ability to customize. It's where we are now. He did the best.
Yes, I have 3 questions. One of them is mine, and the other one is Craig Hoyt, so, because he couldn't be here. So I have a partial knee replacement, and when it goes bad, could I do something like this or not?
There are custom companies now if you had enough lead time. And I should add that knees don't loosen as frequently as hip, far less. The main reason knee implants have to be replaced is pain. So when they put a new knee in, they have to do all the tensioning of the tendons that hold the knee together again. They have to measure the height and hope that it's the same, meaning the height between the tibia and the fibula, the 2 bones in the knee. All of that. And then if any bit of that is off, it's pain. And the question is it more pain than it was before? It doesn't mean you can't walk, but it's going to hurt. And so you're forcing your muscles and tendons to adapt to what has been put in. And unfortunately, all too often, they say, no, it's not worth it, do it again, because it just hurts too much.
So he asked, since the technology for printing body parts has been understood for about 25 years, why hasn't it taken off drastically, in a drastic way?
I can give you several reasons for that. Cost is probably the number one. So can it be, is there enough energy put on it? You get to the economy of scale, and the companies are making money the way they're doing it now. So they don't have tremendous impetus, but if someone is brave enough and sponsors this and builds the company, maybe it's a disruptive type of company, and people say, well, they're getting better results than what you're offering me. My insurance company has to pay for it because it's as good or better than what the other company is selling. With a lot of new technologies, I hate to say this, some companies will buy something that they see as new and threatening commercially, put it on the shelf. So we have to have brave entrepreneurs.
I think you answered his second question, but when will geezers like me be able to replace whole body parts and play sports like he was 25?
No.
How many teams worldwide are working on similar technology?
On point of care or just customization? Point of care, so in this country we only have 3 medical centers, Walter Reed in Washington, the National Military Hospital, Mayo Clinic, and the VA's program on customized parts, and it's mainly for wounded warriors who've lost their limbs, is in Seattle, Puget Sound Hospital there. There's really not any sizable point of care manufacturing happening anywhere else in this country, and there's probably another half dozen in the world where there are physicians ready. I'm thrilled to work with orthopedic surgeons, neurosurgeons, plastic surgeons. They're early adopters. They would love this if it was available, but we just don't have the on the ground. Over the next 10 years, hopefully that starts changing. Please.
What kind of regulatory hoops are you having to go through for point of care, safe and effective?
Great question. So the FDA is not trying to hold this back in any way. I have good friends at the FDA. I'm not afraid of them. I know lots of companies are terrified of them. There's a Center for Device and Radiological Health, CDRH, and it has its own division on 3D printing. They have the 3D printers there. They can try stuff out, and there are several engineers there who understand everything we're doing. I see them at scientific meetings. I look for their guidance. They're happy to talk about things. The thing that companies are afraid of is that binding decision. And the binding decision that says you need 500 patients to try this, that's going to be tens of millions, if not $100 million, to do that clinical trial. They would they'd rather hear that it's not so different than what we're doing now, and it can just be approved, and they can start selling.
So this doesn't have to be considered experimental?
Exactly. If it's considered experimental, then you need evidence that the physicians can base their decision to recommend it to their patients. Exactly.
Twofold question. How many sheep do you do a year? And why do you do the sheep? Is that for the mandibles to study for the human, or do they actually do a lot of sheep?
So this work usually begins with lots of cadavers. So we'll get specimens from the slaughterhouse. They've gone to food and, you know, and skins and so on have been taken already. We're just getting the specimens, the skeletal specimens. Sheep that come to Ohio State. So Ohio State is a great place to be doing this work. Try doing a sheep model in a downtown office building on the east or west coast, or in a really dense downtown area. It doesn't happen. We have an ag school, a vet school. We have a fantastic veterinary facility to work in. We have human scanners, CT and MR, for use with animals. We have our own herds. The sheep we get are from Worcester. They're 75% Dorset, polled, no-horned sheep. They're just almost like it's an inbred rat strain. We know days, old, weight, everything about them. And we will, if I was doing one study, I might study 3-4 sheep, maybe a control. That tells me enough. I'm trying to not use any. I'm trying not to use any live animals for my research, but it just comes down to we're trying to make sure that when we go to a patient, we can help them. Just need to be sure of that before we put it in a patient.
One more question?
Please.
Can you do this with children whose bones are changing and growing, and then put an insert in and then they grow?
Great question. So that's why there's a field called tissue engineering. We need to, so that you've just seen a bunch of metal. Put that in a child, there's going to be revision surgery by definition. With the cranial implants, we've been doing it so long, we've gotten better. They can put springs on them so they can move. There's a lot more sophistication with the skull right now. The hip and knee and the rest of the skeleton is about 10 years behind the skull.